Good evening, and welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here at Kopernik, and it's great to have you all up here today. A bunch of faces I do recognize, but who's here for the first time or not since your fourth grade field trip? All right, a few people. All right, very good. Who here are members? Pretty much almost the rest of you. All right, well, what I always like to point out is that for those that raise their hands second, people with a membership have a valuable piece of information. It's Kopernik membership gets you into any of our programs here for free, but we also belong to what's called the ASTC, Association of Science and Technology Centers, and it's a consortium of over 360 other science centers that honor each other's memberships. So you could go, with your Kopernik membership, you could go to Roberson, you could go to the Corning Museum of Glass, go to the Intrepid down in New York City, or the Franklin Institute in Philly. And in fact, a few years ago, I took my daughter down to the Franklin Institute, and had we paid street price for just myself and my daughter, it would have been more than what a year's membership is up here. So if that's the kind of thing that appeals to you, consider getting a membership. So we've been around for actually over 50 years as a public observatory and informal STEM education facility. Right now we're sort of closing up, or coming to the close of our school programs. We have school groups from all over the region come up for a number of different kinds of programs. But also we do a number of other issues, other programs we offer. We have a very extensive summer camp program that is, we're now starting to, our registration is actually starting to fill up. And so if you've got a child or a grandchild that's somewhere between going into second grade and high school, check out the camps that we've got. They're really engaging. They're all hands-on. They're the day camps, and we have a lot of fun with them, and your student gets to so continue their education throughout the summer. Another thing we have coming up here is Rocket Fest. In fact, tonight's program, I sort of always I tried to work in as a sort of a foreshadowing of Rocket Fest. Every year we have an opportunity for families to build one of those Estes rockets. And then bring it up here, and we'll check it out, and then send you out. If it's ready to launch, we'll send you outside to launch it. Last year, we launched over 150 rockets over the day, and a lot of fun. So right now, we've got over 120 rockets, I believe, already registered, but we still have room in a number of launch windows. And but also, you want to, if you're interested in doing it, you got to do it before or by next Friday. We're actually going to start handing out the rockets next Friday, but also come Saturday morning, the price goes up. So do yourself a favor and get yourself registered for Rocket Fest soon. But one of the things that I really enjoy are these Friday night programs. It's an opportunity for us to actually extend and sort of continue our lifelong learning. And the topics are really varied, and in fact, actually, one of the things we do now is we've been live streaming the programs for the last 6 or so years. So if you go to YouTube and you go to, you just type in Kopernik Observatory, you'll see what's coming up, but also you can see what happened. You know what we have had. So last week we had a talk on science and religions, the pursuit of happiness. The week before that was tick and tick-borne diseases, how drones in the air are making the world safer. Fossils, spring skies. But also we do other things as well. We've had live observing sessions so that if there is a meteor shower or a comet or an eclipse, we will, and if it's clear, we will do our best to, to get that out on the air. And last year there was a lunar eclipse that most of you probably missed because it started at 2 in the morning. But Jenny Carty, our live stream astronomer, who's also driving our live stream this evening, did a time lapse of it, and this is what it looked like. start seeing the shadow of the Earth covering up the moon. Eventually, she'll change the exposure so that we can start seeing the what little light that's refracting through our atmosphere looks like. And here you get that blood moon that happens every lunar eclipse. You also notice that the world did not end. And then the Earth will start to move again and open up, and then she'll change the exposure again. One thing that's neat about lunar eclipses is, again, a full moon is, from an astronomer's standpoint, is actually a real pain in the fourth quadrant, because it's just such a bright object in the air. But it wipes out pretty much, like a full moon pretty much would wipe out almost all but the really, really bright stars. However, when you finally get to a full eclipse and you have that blood moon thing, all of a sudden the Milky Way just pops right out. And so it's really quite an experience. But anyway, we've got a couple of things going on tonight. So we have our program this evening. Also at 9 o'clock and then 10:40, there will be passes of the International Space Station. And so as long as the skies permit, we'll, and if it looks like we're going long here, we may just pause this briefly, run outside, take a quick look at the ISS fly by, and come back in and finish the program. But we're very fortunate to have members of the AeroBing group out of Binghamton University. They've been here a couple times before, and I always like checking in with them to see how far they've progressed, and they get to tell their stories and talk a little bit about their interest in rocketry. And again, being an engineer, I think one of the things that you learn very quickly, you learn more from your mistakes than by doing it right the first time. And I'm sure you'll probably talk a little bit about that. So we got Nathan and crew. Just why don't you come on up and we'll get you started.
Testing. You got me?
Yeah, right.
Perfect. Awesome. Sweet. All right. Firstly, I'd like to thank everybody for being here tonight. We are AeroBing from Binghamton University, and we're super excited to share what we do down at the university. Obviously, we're the rocket guys. So being here before your guys' Rocket Fest and being able to share a little bit of our love for what we do with you is super exciting. Secondly, I'd like to thank Drew and the rest of the Kopernik staff for having us tonight. So sweet. Jumping into a quick little intro. My name is Nathan. I have served as chief engineer and project lead for AeroBing for a long time now. And in about a week from today, I will be graduating and moving down to Texas to continue working on similar stuff to what we do today.
Hello, everyone. My name is Kevin. I have been the simulations lead for AeroBing this past academic year, so including fall and the spring. Going forward, I will be continuing my academics at NYU in this fall, doing a master's in mechanical engineering.
Hey guys, my name is Jacob Goodman. So I actually am no longer in the school, but I did found AeroBing in my junior year. And then afterwards, I moved to Texas. I worked at Lockheed Martin as an aeronautical engineer doing simulations for about 2.5 years. And now I'm actually back here in the Southern Tier as the founding engineer for a company called ChipAd.
Perfect. Thank you, guys. So, quick agenda for tonight. Very quickly after this, I'm going to pass the mic right back to Jacob. Jacob's going to talk a little bit about the founding days of AeroBing, kind of establishing some of the relationships and his experience leading and developing AeroBing's technologies. After that, we're going to jump into a little bit about what we do currently in our research. Kevin's going to cover simulations, and I will cover the cool stuff after that. Sorry, Kev. And then we'll jump into a Q&A where we can kind of show off a little bit of hardware. All I ask is that, I know if everybody wants to come up and see, just ask before you touch. We do have some gloves because we do have some items that have survived very energetic events that are better to touch with gloves. But everything here is safe, and we're happy to show it off. So Jacob, passing to you.
Cool. All right. So I'm just going to give a quick couple minutes of kind of how AeroBing was founded, what we did, how we did it. The cooler part of this presentation is what they're going to be showing you guys, cool rockets, videos, explosions, stuff like that. But I'll give you guys just a couple minutes of some of our history and some of the more funny stories that happened along the way. So we actually started, this was kind of a group of guys who were really interested with airplanes. I'd say maybe this was 5-6 years ago. This was my sophomore year. I had a friend who was pursuing his light sport pilot's aircraft license. And so we eventually got it. We went flying a couple times, and we're like, we need to get more people involved in this. This is really cool stuff. We had a lot of other friends who also thought airplanes were really cool. So he founded the organization called Be Above Aviation Society. And so we'd go to the airport, we'd go and talk to people, we'd have kind of info sessions on here's how you can get your pilot's license and all this cool stuff about airplanes. And then we actually submitted a competition. We joined a competition. I forgot what it was called, but it was to build a small little 2-stage rocket. And unfortunately, that rocket launch got canceled because of COVID. But I was looking at that, and I'm like, competitions are cool, but we want to go higher. The problem with competitions is they'll say, hey, you got to launch to 5,000-6,000 feet. You can't actually go any higher. We said, screw that. We want to go to space. And so I ended up going and founding AeroBing at the time with the express goal of sending a rocket into space. And now we're here. So what happened between then and now? So founded AeroBing, and we basically said, okay, we've built tiny little rockets. We built Estes rockets. We built rockets from kits. How do we build a rocket that goes into space? And we sat down, and we just started trying to build rockets. I had a couple of friends who were really, really into it, brought them onto the team, and we sat down in our dorms late at night, and we put together all these wacky designs for rockets that I can tell you right now, if we ever tried to launch them, they would not go very far. They were pretty terrible. And it's actually very funny because I'll look back at some of these rockets and say, who designed that? And it would be me, of course. But we kept pushing, we kept designing things, and eventually we built a little prototype of a motor that we wanted to go and test. And this is where it kind of gets funny. Well, we have this rocket motor design. We haven't built it yet. And where do we go and test that? Rocket motors, when they're done safely, they're safe. But when things can still go wrong, we need to be able to prepare for that. So we said, we're students, we're going to do this safely. So we started calling around fire departments and said, hey, we have this rocket motor that we want to launch. We found a little plot of land. Can you guys come and supervise in case something goes wrong? We thought we were being safe. Well, about a week later, my friend and I, we get called into the university police department. And they say, hey, we heard you guys are making rocket propellant in your dorms. And we say, uh-oh. For the record, we were not. But somehow word got back to UPD that we were doing this. And so we got called in and interrogated by the police over this. And eventually we explained the situation to them. And we said, this is actually what we're doing. This is where we're doing it. This is how we're doing it. We've got the school involved. Said, okay, fine, you guys are safe. And we ended up, it's very funny because we actually ended up getting written up in the police watch section that weekend. And so I called my mom and I said, hey, Mom, I get written up in the newspaper. She's like, oh, my God, that's so great. What did you do? I said, it was actually the police watch section. We got interrogated by the police for making rockets. It's like, oh, boy. But from there, we were actually able to establish a connection with the town of Binghamton Fire Department. And they've been super helpful ever since. They supervise all the stuff that we do to make sure it's done safely and properly. And they absolutely love it. We love them, they love us, and it's been an absolutely amazing relationship ever since, and probably one of the more important relationships that's really helped us unlock all of that we've been able to do with all of our rocket motors and our rocket launches. So that's how we actually got to be able to test our rockets. And since then, we've been able to grow. So we've been able to outreach to other organizations, Kopernik being one. They've been great. It's been great to come here and talk to people about rockets, like-minded people about rockets. 'Cause who doesn't like rockets, right? And so we've been able to do that. And then about, this was December 2022, we actually got to the point where we raised enough money and designed enough rocket motors and blew up enough rocket motors and successfully fired enough rocket motors after learning from all of our mistakes that we were actually able to travel out to California to a launch site called Friends of Amateur Rocketry and launch an actual rocket much higher than we could ever launch around here, right smack in the middle of the desert. And since then, just in my tenure as leading AeroBing, we were able to actually make 6 trips out to California and launch 7 high-powered rockets. And so I think I've been absolutely amazed to see how much success AeroBing has had in such a short amount of time. We're scrappy. We don't have a lot of money, but we figure out a way to do it, and we figure out a way to do it right, and figure out a way to do it well. A lot of other schools have huge amounts of funding, tens of thousands of dollars of funding, and huge donors, and we didn't. But we still figured out a way to make it work, and a way to do it just as well, if not better, than some of the many other schools around the country that have rocket programs. I think one of the things that I really took away from AeroBing, obviously, I love rockets. I love blowing them up. I love launching them. It's always a huge amount of fun, a huge blast, and a great learning experience to do. But it was also great to be able to train guys like these guys, and be able to one day hand them the ropes and see just how much cool stuff they've been able to do since. It's been incredibly fulfilling. It's been incredibly impressive. And so with that, I'm going to hand it back to them so they can tell you about all the cool stuff they've been doing.
Thank you very much, Jacob. Without Jacob kind of embodying like the JPL movement of just keep pushing through, none of us would be here today, and my past 4 years would be a lot more boring and a lot less energetic. So big shout out to you, and
Go.
we got a little flame in there just to keep everybody's attention. All right, we're gonna jump into simulations, and I'll pass it to Kevin.
Hello, everyone. So AeroBing has to do a lot of testing, whether that be physical testing or software testing. One of the main ones that we do is software testing, that being simulations. So AeroBing utilizes various amounts of tools to do these simulations, and I'll explain each 4 of them that are listed here. First is RAS Aero, then Open Motor, then something with a really long name that many of you might not know, Computational Fluid Dynamics, or CFD for short, and then another one, long name again, Finite Element Analysis, or FEA for short. So, simulations, RAS Aero and Open Motor. What are these names? So RAS Aero and Open Motor are basically simulation tools that allow us to design and test these plans that we have for our rockets. Rocket geometries can be adjusted in these software and also give us rough estimates of how it would perform during flight, which is going to be very important when we maybe try to talk to FAA to see if we can launch this. Key outputs for RAS Aero and Open Motor are velocity, altitude, stability, and thrust. Data from live tests that you'll see later on can be imported into these software, which allows us to get even more accurate data for seeing how our rockets will perform. So CFD, the one with the very long name, Computational Fluid Dynamics, is basically a solver for fluid flow equations around a 3D model. So it basically takes these equations for a small fluid particle and puts an average on a bunch of them and then puts it through a 3D model. So in this way, we can figure out how would the aerodynamic performance of our rockets come to be. It results in a contour, so if anyone here has seen the weather, which I'm pretty sure everyone has, in the weather, the weatherman or weatherwoman will show the state or the country in different plots of colors and how the temperature changes, and it'll be red for a high number, blue for a low number. This is the same thing, except for something like speed or pressure or vorticity or larger names that you might not know. This allows AeroBing to simulate various rocket designs and get an understanding, okay, what is the shot going to look like for this fin design? What is the shot going to look like for this nose cone design? How does the drag occur for this design, and so on. So I have a little video here. It's very fast, 8 seconds, but it's basically showing how shock waves are created on this Mach 3 speed against one of our designed rockets. You can see the lines of shock waves forming, and then the red showing high speed, blue showing no speed or low speed, and so on. I'll play it again. It's very quick. But yeah, it's really cool, and I love doing simulations like this in AeroBing and then teaching people how to do simulations just like this. It gives a really good visual to people to understand, okay, what is the speed this rocket's going, what's happening in the air, and so on, and how that can improve our designs going forward. So, going from something that shows us how the aerodynamic performance is just from air, how do we see how that will affect the rocket structure itself? So this is where we get into the finite element analysis portion, which basically just calculates the deformation, stress, strain, how the rocket will break or bend during the loads as it goes up. It also provides another contour that gives a visual representation of how these forces break this rocket. This allows AeroBing to understand, okay, our rocket will break in this way, maybe we should update it and redesign this. Our fins are not going to stay on the rocket at this speed, so maybe we should make our fins bulkier, and so on. So this is another little animation showing you how the rocket would deform at like Mach 3 flight and so on. As you can see, the colors start changing, the rocket starts to bend, and yeah, comes back. Well, this coming back is just the end of the animation, but it's to show that we can get an understanding, oh, this rocket will bend in this way, so thus we might want to use a different material at this force, at this speed, and so on. So yeah. Oh, that's it again. Next slide. Okay, pass it on to.
Thank you, Kevin. Kevin's one of my favorite guys because he takes care of the hard math while I get to do the fun stuff. So my bread and butter and some of the stuff that I've spent basically 4 years working on throughout AeroBing is working on developing our motor, right? So a big part of the rocket is what makes the rocket go up. In the past, AeroBing has done some launches where we have not tested our motor, and bad things have happened. Generally, we like to go and test things before we actually go out to California and fly them from the standpoint of stuff gets expensive if we have to fly out every single time for every single test. So luckily, one of the things that Jacob passed down to us is a great relationship with the Binghamton Fire Department. We have absolutely utilized every second of that relationship. Fire chief knows that when he gets a text from me at 11 p.m., it's usually not a good thing. But through that relationship, we have been able to set up a stand like this. The purple here is basically a bunch of steel piping that we have welded together, and it is currently buried in the field out at the town of Binghamton Fire Department with around 400 pounds of cinder blocks, concrete, and steel stood behind it, and it's all cabled to the ground. So through that, we take hardware here that we are not intending on flying. We make our propellant here, and we actually get to go to the town of Binghamton Fire Department and test it here so that we can get away with figuring out if there's a flaw in our design before we actually have to go out and test it. So we'll get to some videos soon, but this is kind of what that setup looks like. And the model that is on this page right now is actually sitting right up at the front. So when the Q&A comes around, we can pick that up and bring it around a little bit. So a big part of what we do is solid rocket motors, right? So what that means is that our fuel is not liquid like you might see in a Falcon 9 or a Blue Origin rocket. Our fuel is actually constituents of rubber, aluminum powder, and a solid form of oxygen known as ammonium perchlorate. So when we're creating our rocket motors, part of the way that we control or throttle or kind of decide what the profile is going to look like is we can actually shape what that grain looks like because it becomes a castable entity, right? So up there in the black and blue right at the front, that is what's known as a mandrel. So that was actually sitting inside of the rocket motor to the left of it while we were pouring rocket fuel into it. And then when it hardens, we can pull it out and we're left with a negative of that or a shape that we can use to control what the thrust profile looks, right? So for rocket propellant, there's a couple big properties that we aim for. Number one, we want it to be very, very thin. The reason that this happens is because when we actually pour it into the rocket motor, if there's bubbles in the mixture, those can cause the rocket to explode. And while we've had several moments like that, it's not something we strive for, I promise. Another thing that we strive for is we don't want to make the rocket fuel too thin, because if the fuel's too thin, there's probably not a whole lot in it. And by having more solids than liquids in the actual fuel, we get a higher efficiency. So by making sure that we can get more efficiency into our propellant, we can make the same rocket of the same size, of the same weight, go higher and faster. And that's building towards the goal of a space shot. And another big aspect of this is that we are students. We do not have endless bank accounts, and the school does not give us nearly enough money, so it needs to be using readily accessible components. So everything that we make is purchasable online from 1 or 2 websites, and there are some other components that we do not have access to, so it has been a ginormous engineering challenge to kind of work around some of these constituents and still figure out how to do what we do. So the first video I'm going to show is just demonstrating kind of like how thin this is, and for reference, in this mixture, by mass, it is around 83% solids. So what that means is that we pour basically granules in it, and 83% of the total mass is solids, and you'll see that it still flows pretty nice. That was my buddy Luke going for a poke. I stopped him though. And next up on this video is actually the process of pouring the grain. It is as simple as it sounds. We have a funnel at the top of the motor, and we take the big bucket full of energy-dense material, tip it on its side, and pour it down the side. save you the full video, but there was about 30 pounds in that motor, right? So moving on to kind of like more of the hardware that we make, right? There's a couple goals with the hardware, right? So beyond just making sure that we get as much energy as possible into the motor, a big goal is to keep everything light, because by keeping everything else light, there's less force wasted on mass and everything else, and we can just use that same amount of actual energy inside the rocket motor to just make it go faster versus carrying stuff that we don't necessarily need to carry, right? Beyond that, a couple main goals. We want to keep the heat where it's supposed to be. Our motors burn at just shy of 3,000 Kelvin, or it's like north of 5,000 Fahrenheit. Next up is to keep the pressure where it's supposed to be. This motor up here hit a peak pressure just shy of 1,500 PSI. And the third goal of our hardware is just to stay where we want it to be, right? So with the static tests, they're supposed to stay static, right? All of these are a little bit of subtle foreshadowing, so stick around, we got some good videos. So next up, right? A big thing that we try to practice and teach through AeroBing is, like as I said before and Jacob said, we do not have $1 million. We are not NASA. We cannot send out parts to get machined in Wyoming and rush order them and get them 3 days later. Luckily, the university provides us with what's known as the Watson Fab Lab, which is basically a giant room full of tools and machines that you walk in, you get handed the keys, you get a little bit of training, and they allow us to make our own parts. So there are limitations though, right? We do not have the $5 million machines that you might see in very specialized shops. So a big part of what AeroBing students have to do is we have to design around what we can make and what makes sense to make, right? And that's really good practice for industry, because it's not very often that you'll get to a job and they'll be like, here's the P card, go wild. Usually there's like limitations for the scope, the price per unit, and stuff like that. And AeroBing has to deal with those exact same problems on usually actually a harder level. So beyond just being limited by the machines, a vast majority of AeroBing's parts are actually machined by the students. We do have shop techs at the shop that are there to help us and teach us, but AeroBing really prides itself on getting students that are capable of running the machines and teaching them how to do it, and making sure that when the time comes and we need a part, we can get it done, versus having to wait in queue with other teams who may opt to use the technician's time. So on the picture screen right here, we have a couple parts. On the leftmost is a coupler, which I think is actually the one up there, and I'll pick that up and show it around in a minute. But essentially the main job for that guy is to make sure that the motor or the propulsion stays attached to the nose cone and the aerodynamic structure. Next up on the middle slide is a nose cone tip, which goes at the very front of the rocket. We actually have one of those. I left it in my car, so I'll get it a little bit later. But the main job of that is to keep the shock wave at the angle that we want it to be, firstly, and secondly, to absorb some of the heat so that the structure of the nose cone, which is primarily fiberglass or carbon fiber, does not have to take the brunt of that, because composites are great in strength, but they're very bad when they get too hot. So next up, because of the really high temperature of our rocket motors, usually we have to use some really unique materials, right? So there are very few metals that exist, if any, that can survive the temperature that our propellant burns at. So we use a combination of techniques to kind of maintain the structure while also making sure that the heat stays where it needs to be. Remember, I said one of the main goals is making sure the heat stays where it needs to be. Subtle foreshadowing. So on the left, we have a picture of our closures, right? So on the left of the left image, this guy right here, this is known as a forward closure. This goes at the very top of the rocket motor, and it's basically just a flat plate with a piece of phenolic on it, the brown stuff that kind of looks like wood, even though it's not wood, I promise. And phenolic is a very good insulator and what's known as an ablative. The main job of that closure is to make sure literally just that the pressure stays there and that the phenolic absorbs a majority of the heat before it hits the metal behind it, shiny part right here, which acts as the structure. So this is a unique kind of combination of materials that uses phenolic as the thermal side and the metal as the structural side. Moving a little bit to the right, and we got a way bigger version of that right here, is a nozzle, right? So on the contrary, there's a giant hole in our nozzle. We're not trying to keep the pressure in right there. We are trying to choke the flow. So right in the middle, there is a little gray piece, and that is actually made out of solid graphite, kind of like the same stuff that you'll have in your pens, excuse me, not your pens, but your pencils, and you write with. The really great factor of graphite is that graphite does withstand the temperatures of our motors. The really bad part about graphite is that graphite, when you use a ginormous block of it, it likes giving heat out to everything, and it likes forming gradients that make it crack. So this is another unique combination of materials where we get the properties of phenolic that stop the heat from going where we don't want, and we get the graphite, which kind of holds the shape so we can have a constant in the motor. So also in AeroBing, we use a bunch of 3D printing. 3D printing is one of those really unique technologies that allows us to get shapes that we may not necessarily get to get otherwise. And like I said before, right, so that mandrel, the blue and black thing up there, that is a shape that we simulated, and it would be something that would be very, very difficult to get without the use of 3D printing. So by 3D printing that shape, we were able to get a complex taper, a complex shape, and in the length, and for probably less than $20, right? So that's one of the things that 20 years ago, students would not have access to, and they would have to find another workaround. So by using technology like 3D printing, we have totally been able to make our motors more advanced and better for all aspects, right? So on the far right, this is a more advanced nozzle for a future static fire that has been further mass optimized, and we'll talk a little bit about that one more later. So next up, right? So another aspect of hardware is that the casing for our motors are traditionally aluminum, and aluminum has a very, very low melting temperature. And going back to those main goals, right? We want to be able to keep the heat where it needs to be. So AeroBing has this problem where we want to be able to scale our motors up, right? So what we're seeing right here, that motor, we launched a version of that to an estimated 70,000 feet in December. So the Kármán line, or space, is around 5 times more than that. So we do need to go a good bit bigger. And as we scale up in diameter, buying commercial parts becomes way more expensive. So we have been trying to design our motors and our hardware around the ability to manufacture things on a much larger scale. So there are some things that we do on our smaller scale motors that may be counterintuitive, but the idea is to test the technology so that we do need to scale up. We're ready for it. We have a solution prepared, and it does not become a roadblock that we have not thought of, because we always want to be able to test like we fly and fly like we test in the future, right? So this is one of my favorite solutions for a really tough problem, and it's known as spin casting. Essentially, on the inside of the motor, you'll see a little bit of black layer in there, right? It's obviously not just straight aluminum on the inside. So what we do is we use another mixture of rubber, and instead of adding fuel and stuff that's going to burn, we add fibers that are going to hold it in place. We add materials that are going to slow down the burn, and materials that char up. The main idea is that we're lining the inside of the motor with something that's not going to let the heat through. And the issue is with buying this stuff is that you usually get poor tolerances. So the OD of the material and the ID of our casing can usually be very different, which becomes an issue when you try to static fire the motor. So what we do is we actually mix this as a liquid, we spin up the casing, and we pour it inside. And I'll go ahead and play that. So this is after we have put the material in there, and we start spinning it up so that it allows it to kind of evenly coat. It kind of turns it into a centrifuge that gets us even thickness, and it allows us to predict how thick we're going to make it also. So this exact technique is also really good because it becomes modular, right? So if we need more insulation in one place than we do in another, we can just pour more in one area and then inhibit where it flows. So by doing that, we actually get a better solution than you can find just by buying a commercial item, right? We can control certain aspects for exactly what the motor needs and further reduce our mass. All right, I'm done talking for a second, all right? We're going to jump into the good stuff. So these are 2 motors that we fired. I think the one on the left, which we'll play first, was April 2024, and that was a motor named Sally. Sally fired for 6 seconds and made around 6,000 newtons of force peak. And remember, all of this was done locally at the town of Binghamton Fire Department, right? So coming up first. Yeah, so we usually have that cinder block wall up for the purpose of if the rocket motor decides to spit something out, it's there to send fragments away from us. Obviously, we underestimated how powerful this motor was going to be, and it was a very funny experience we were standing a couple 100 feet away, and I'm on FaceTime with a friend, and I watched the cinder block wall fly away, and I'm like, I'm going to have to let you go. So for the next static fire, we opted for just a little bit more distance between us and it, and a little better, yeah, and a little bit of better anchoring for the motor, so if God forbid something happened, we still had some form of protection. This motor, which is sitting up in front of us, named Sabrina, hit a peak of 14,700 newtons, or enough to lift up a couple cars. So it was super duper powerful. It hit 1,500 psi, and that burned for a lot less time, but consumed the same amount of fuel. So you just get that force a little bit quicker. So following that static fire, we built a version of that we flew out in December, and we'll show that in a little bit later. But the really funny part about the static fire is that I'm a believer that there's really bad juju if you design the motor and you press a button. So it's kind of a tradition that when we're static fire day, usually we have a young guy get to press a button, and they usually don't know until the day of. So about 5 minutes before we static fired that, I gave it to one of the younger students, and you can hear like kind of like get a little shaky during the countdown. So it was like 5, 4, 3, 2, 1, go. So, but yeah, so the static fire days are super fun. We usually have a team from the fire department out there kind of helping out just in case. They have fire extinguishers. They have like the whole fire engine out just in case something happens. And the interesting thing is, like, our directive for these kind of tests is that if it explodes, do not try to put it out. You will not be able to put it out. If something else catches on fire, then we approach. So next up. So remember when I said there's a little bit of subtle foreshadowing, right? So this was a motor named Madeline, which was fired, I believe we made this my sophomore year, I think it was fall semester. And this is a good example of, I was talking about the insulation on the case and the spin casting. This was a good example of a failure in that mode, right? So you'll see, it starts looking good, and boom, you have a flame going out the side. Generally, that's not what we want. We usually just want the flame going through the nozzle. So yeah, that thing proceeded to burn itself to the ground, and half of our test stand also. But you know what? The best way to learn these things is to make the mistake and be able to move on. I can promise you that I have learned far more from cutting open motors that didn't work than cutting open motors that did work.
How was it able to blow off the side?
So the insulation failed. So it's the entire length of the motor has propellant that's on the inside burning, and if there's an area of the insulation on the inside that is maybe has a bubble from the spin casting process or just isn't sealed correctly, and it burns through that and it hits the aluminum, it will basically instantly go through the aluminum. Like,
You verify that everything's 100% before you run it?
yeah, there's still unknowns. There's still parts of assembly that, like, you know, unfortunately the school doesn't like us bringing 10 pounds of really energetic material to their X-ray. So we can do things ahead of time that allow us to inspect them, but generally during the assembly process, whatever happens is kind of what happens. So unless there was something that like we explicitly knew wasn't going to work, we usually static fire it, right? So getting rid of propellant is a very large challenge. So generally we static fire it unless there is a known issue or a safety risk or something like that. So beyond just motors, one of the favorite things is rocket launches, right? So this is kind of the culmination of everything we do. It is maybe the most fun and the most stressful week of my life from the standpoint of it's usually me out there with 10 younger guys who are all very, very excited, but at the same time, it is a great experience being out there with 10 younger guys who just happen to be some of my best friends. And also, we all want to see this thing work, so everybody understands that, like, when there is a conflict or something, we all kind of just have that moment where you just like look each other in the eyes and we're like, we're here to have this thing be successful. That is top priority right now. So unfortunately, we can't do our launches in New York State under threat of felony and 10 years imprisonment, I guess. But at the same time, true to our core, everything here is built in Binghamton. The propellant, the casing, the nozzle, the nose cone, the fins. We do everything ourselves. The flight computers. It's kind of one of our prides, right? You know, when we're talking to people in industry and they're like, where did you get X, Y, and Z? And we can say, you know, see the machine down the hall? Yeah. We started off with a giant piece of metal and turned it into this, right? So that's something we really pride ourselves in. But the actual purpose of the rocket launches is, firstly, a test of logistics, right? Can we pull this off in the time frame that we expect to and do it without anybody getting hurt, which is a ginormous one, without any accidents, and while still being able to complete our objectives, right? And our objectives are never a perfect launch because, in my opinion, there's no such thing. The objectives are getting the tests that we want done, right? So understanding, did our structures perform? Did our recovery system perform? Subtle foreshadowing. So our rockets live by a saying, keep it simple, stupid, right? So we want to make sure that we go into these things with the best possible chances of success. And a big part of that is every single part that we make and that goes in the rocket gets asked about 4 times. Why is this here? Does it need to be here? Can it be smaller? And can we replace it with another component that might be able to mesh 2 parts into one, right? So this is a rough breakdown of our rocket, right? So starting from the top, a little subtle foreshadowing here. There's a single battery powering redundant systems. That's not redundant. Moving a little bit down is AvBay 1. AvBay 1's main job is to communicate with us on the ground, right? So we launch our rockets to usually very fast speeds and very high heights, right? And a big part of that is that by the time this thing's done with its boost phase, which is the stage where the motor is actually burning and pushing this thing to a faster speed, we usually cannot see it by the end. So this is not like an Estes rocket where you can watch it the entire time and see, oh, it landed in Paul's tree over there, right? It's not like that. We need to have multiple GPSs and downlinks, basically antennas that communicate with us downrange and tell us where everything is. So AvBay 1's job is solely there to say, hey, I'm the rocket. This is where I am, through an antenna to us on the ground, no matter where it is. We'll talk a little bit more about AvBay 1 in a minute. Next up is the recovery chamber. The recovery chamber is where the actual hardware to make sure that we get the rocket goes. Essentially, our rockets, they're not Falcon 9s. They don't come back and, you know, propulsively land themselves in the GPS predicted coordinates. We have a parachute in there, right? So we have a singular parachute, a couple of Kevlar lines, and a couple of black powder bulbs in there. So essentially what would happen is once this rocket gets to the top and it senses that it's no longer going up, it would detonate a black powder charge that would separate the nose cone and pull out the parachute in a perfect world. Next up is AvBay 2. AvBay 2's job is to, firstly, get video, because nobody believes it if there wasn't a video, right? So we gotta get a video. And also make sure that black powder bulb goes off at the right time. Luckily, AvBay 2 was on a redundant power system. Next up, below that, is something that we just spent a lot of time talking about. It's the solid motor below it. So our rockets are really, really simple for the purpose of we are optimizing for speed and optimizing for altitude. AeroBing was built on the goal of going to space, and the best way to get there is to minimize everything else except for that. We do put some payload in it, usually like mementos from people, you know, pictures of girlfriend or a letter. We haven't gotten any of them back yet, but we're working on that, I promise. So once again, I'm done talking. We got some cool videos. This is what it's not supposed to look like, right? So you'll see we obviously have a very fragmented part of this rocket sitting right here, so that's a little subtle foreshadowing for you. A little rapid unscheduled assembly didn't hurt anybody.
4, 3, 2, 1, ignition.
I think so too. So this is always such a funny video for me to watch because I remember my
Ignition.
my initial thought behind this was, oh no, it exploded. And then the next thought behind that was, wait, that means I get to build another one? So that's kind of how it goes, right? So immediately after the launch of this pink rocket, which was named Margot, kind of collected all the scraps. We realized, wow, we have 25 pounds of rocket propellant and nothing to do with it. What do we do now? So we put it in a fireplace and lit it off.
There's a parachute.
Oops. A little too far.
Margot.
Said bye-bye, Margot. So we get our flames either way, right? I don't know if this video goes that long, but the fireplace was glowing red by the end.
Dude, look at the fire pit.
Sorry.
There's a few seconds in there.
So next up is what it's supposed to look like, kind of, right? The subtle foreshadowing is will be explained afterwards because it's not visual, right? So Mary was our most recent rocket,
Dude,
which
look at the
used
fire
the
pit.
Sabrina motor with basically fins glued on the side, a couple of av bays in there, and a really beefy nose cone. And it was estimated to go 70,000 feet in Mach 4. Estimated. We'll get there. And this was that launch. And that was the last we ever saw of her. So, like I had said, right, and pointed out, we had redundant systems that were supposed to downlink to us, basically radios. The idea was that if one of them stopped working, the other one will still be able to communicate with us. For some reason, this guy named Nathan made the executive decision to power them both off the same battery. So when both of them stopped communicating with us, the second we pressed the launch button, there was only one guy to blame. But like I said, we learned a lot from this trip. So we were able to verify that this rocket made it through what's known as max Q, which is essentially if the rocket's going to destroy itself from aerodynamic pressure, it's going to happen then. But we visually saw the rocket go through that phase. We saw the motor work. So a whole bunch of stuff was accomplished during this trip. And we have left the younger generation with a ginormous mountain of logs and information about what we did, in addition to actually really trying to involve our younger students with the build so that when the time comes and they need to do it, they can do it better, right? The idea is never that we're going out with a bang, it's that we're leaving the next students with the architecture of our successes and the information for our failures. So, daily double / bonus slides. Another thing we do with the town of Binghamton Fire Department is range training, right? So, as you can see and hear from a couple of our videos, we deal with a lot of stuff that can be incredibly dangerous if it's not operated and used correctly. And one of those things that we do to prevent accidents from happening is range training. Range training is one of my favorite days of the year, just because we're going out to the fire department and we're either lighting something on fire or blowing something up for no other reason than why not. So the town of Binghamton really does help us out, so ginormous shout out to them and Chief Lewis. They really have never said no, even when they probably should have, and they just ask us how they can help us do it safely, right? So for AeroBing, safety really is a top priority. This is something that we're all super passionate about, but we have a flawless track record for safety, and we don't want anybody to get hurt in the pursuit of a space shot, right? So one of the big things that we really harp during these events is that this is all about communication. We want everybody to know what everybody else is doing at the same time. To make sure stuff goes safe, generally we have what's known as a range safety officer and an operator. These are the two guys that when you hear them talk, you kind of just zip it and throw out the key. Because these two guys, when they're communicating with each other, it's usually super vital that they're understanding what's happening at the other end. Because we are at a field. Generally, that communication is happened by yelling and making sure the other person hears it. So those communications are usually relayed back. So, you might ask something, they might confirm, and you say, understood that is happening, right? So through that, we have been able to do a whole bunch of fun tests. I'll show a video of one in a second. That their primary goal is just making sure that we maintain the safety and further protect our range and our students. So this is one of my favorite videos. This was from a range training we did a couple months ago. The main goal of this was to go out, get a couple new kids familiarized with how we do our communications and how to proceed with the procedures, right? So this was around 450 grams of catalyzed copper thermite in the middle of the field, because why not? And then you can see little chunks of iron oxide and copper just flying down. So I think that's all we got for you guys tonight. Do we have any questions? Are you going to pull up the chat?
All right, first question.
first question is, what happens to these things when they come up and come back down again? Do they burn themselves up, or does somebody find out that this is coming through their house? Where does the stuff land?
So that's a very good question, right? So luckily we do our launches at the Friends of Amateur Rocketry out in California. It's basically a tiny little site in the middle of a ginormous desert in Southern California. So when we launch, we actually do dispersion analysis that basically tell us what's the maximum distance this rocket could go in the worst case scenario. So not only is it very, very sparse, we do analysis that makes sure, you know, we're not going to land in the middle of the 10 during LA rush hour, right? So we do those, but with respect to where they land, we don't exactly know. We kind of just get a radius of prediction, right? So stuff like wind, stuff like weather, stuff like how straight the rocket goes off the rail, they're all factors in that.
And so I saw you were standing under sort of a little ceiling, so to make sure that it didn't land on you. Cute.
Correct.
And the other is a really dumb question. Who are Sally, Mary, and Sabrina?
It's a very good question. So generally, the choices for the names, excluding a couple stints of ex-girlfriends, which we have advised the younger students not to do, they were named after kind of like either pop icons or people that have inspired us, right? So Sally was named after Sally Ride, who was the first American woman in space. And Sabrina was named after Sabrina Carpenter, because I really like Sabrina Carpenter. I will take the blame on that one. And Mary was named after Mary Elizabeth Winstead, which is my buddy Luke's favorite actress. So kind of just like we have like a little circle of the naming scheme that gets passed around. So
There was one male name also that I didn't remember.
There was a male name as well, or no? No.
I don't think so. Yeah.
What?
Margot, yes.
Margot.
Yes. That was Margot Robbie. So that's the pink one up here. R.I.P. Margot.
All right, we do have a question from the chat. It says, do you use FDM 3D printing, and if so, what kind of filament do you use?
Oh, that's a great question. So yes, we do, right? So this mandrel up here, the black and blue one, that was FDM 3D printed. And as for the filament that we use, it's very dependent, right? Like most good questions, the answer is it depends. For this one, it was PLA, just from the standpoint of it didn't need to be super structural, and that we needed it quickly and cheaply. So for other stuff that we fly, it's usually some form of polycarbonate.
All right. Another question? All right.
Sorry about this.
You're all good.
Territory. Are you taking the pictures from above with a drone, or is there some sort of a fire thing that is looking down upon you?
Yeah, we have a member with a drone, so he gets cool like aerial shots of the tests, and this was a good shot with kind of like the team and some friends there.
And it will stay stationary enough not to?
Yeah.
Oh, amazing. This is fascinating.
Cool stuff.
The question over here.
Since the ultimate goal is to have a rocket that can reach space, it will require more money and things like that.
Mm-hmm.
Do you think you will hit a threshold because of lack of funding and resources, which will prevent you from reaching your objective?
Yeah, that's a great question. So AeroBing is very broke, as always. We're college students. We live off of ramen noodles. I remember watching the pink rocket blow up, and you know, my third thought after, oh yay, I get to build another one, was there's 7 weeks of ramen noodle paychecks. But yeah, so we're always reaching out to community members, industry members, trying to help us support our vision, whether through monetary or in-kind donations. But yeah, we have been stagnated before, and honestly, the interesting part of that is that it has led us to new, unique solutions. So it's not always a bad thing that we're the broke college students. It's honestly one of the good things that has inspired us to innovate and find solutions for things that haven't really been considered before. So it's a blessing and a curse.
I'll also like to add on to what Nathan was talking about. As we make these small milestones, however small they might seem, we get more fame, notoriety, trust from the school, which allows us to start propelling ourselves, not only the rocket, but propelling ourselves and the club to gain more members, and gain more people in general to want to support this initiative, support this mission. So as we make these small missions and small like adjustments and new things, more people join, and then we get more funding, and so on and so on. So it might seem like, wow, we're really broke college students that we're not going to be able to ever get to space. But as we do this small little test, whether it fails or it succeeds, we also gain more ability to do that opportunity that then gets to our mission. So it's almost like the upwards trend, both in the fact that we're making better and better rockets, and also the fact that we're getting more opportunities to do this thing, which is cool.
Another question over here.
You mentioned that there are other colleges, schools in the country that have programs. Do you have any idea how many there are, and do you collaborate among yourselves?
It's a good question. So there is, how many there are, I could not possibly count. I think most major universities have a team. They don't always go as broad in scope as us. Some of them are teams that mostly buy components and piece them together, whereas we kind of pride ourselves in the full stack engineering process. But as for communication, yeah, I mean, there's some, it also depends, right? I have some very good friends at other universities that do stuff very akin to what we do, and we're always very open book with each other and with the community. But there are other universities that kind of operate more under a IP/industry secret style, which I'm not a big fan of, but at the same time,
So
they
you're
exist.
more open source, if you could say.
Yeah, there's certain things that we have been advised not to share. Like, let me go back a little bit here. Yeah. So our propellant name for our last rocket was Go-Go Juice, and as you can see, these are not the real ingredients there. And that was on advice of the university lawyer. But I mean, generally, like the practices of what we do and how we do it, we do not have a problem with sharing.
All right, got a question here.
What percentage of your launches exploded?
Ooh. A majority of them. A vast majority of them do not work. But as I've said before, right, I learn more from when stuff doesn't work than when it does. When stuff works, it's honestly a little boring. Exactly.
Yeah.
What is the most unique failure that your rockets have had?
So this one was not pictured, and this wasn't a rocket. This was a test we did we did a static fire, right? And for some reason, actually, I didn't have a video of this up. It's a pretty funny video. We made this motor beginning of my junior year. It was named Charlie after Charlie XCX, right? You know what's up. And that motor was made out of a composite tube, right? So it was not a metallic tube. It was fiberglass for the casing and like the pressure vessel. And for that motor, our nozzle was held within the motor with JB Weld, like the same stuff you can buy at AutoZone, right? It's a very powerful glue, but was evidently the wrong choice for this. And about, I think it's a quarter second into the burn, you can actually see the nozzle fly out and hit the deflection wall and get shot out. And there's a picture of me on the field holding the nozzle going. But yeah, so that was an interesting one because it proceeded to burn. So all the propellant inside of it just kept burning, and it kind of turned into like the world's most expensive road flare. And if you stick around, I'll show you a video of that. It's pretty funny.
Another question.
But the softwares for simulation, are they open source or they?
Great question. I love the simulation questions. There are open. Oh yeah, sure. Sorry. Oh, yeah, sorry. Great question. I love the simulation questions. There are open source versions of CFD, computational fluid dynamics, called OpenFOAM, and there's other ones online as well. You just look up CFD free solvers, you'll find it. FEA as well. There's also FreeCAD there's 3D modeling software that's free. There's a lot of softwares that do the same things. There are some that are free, some that are paid. Of course, the ones that are paid are probably a little bit easier to use. You know, they've had that effort put into them, that they're easier to run and so on, and that they can scale to a very large computational load and accuracy. But you can definitely do your simulations for free, completely for free. Find YouTube videos on how to do them and so on. Yeah. These were not open source though. They use a software called ANSYS, which is free for the school if you're a student, but you could definitely do them open source. But I'll let Jacob
Yeah, just a quick note on software. If you're interested in downloading software, Autodesk has a really good student program, even if you're in high school. I've had Autodesk software since 9th grade. So using just like my high school email, they basically gave me a copy of every single software they sell. So I would totally recommend getting your hands on some of that software and just figuring it out. There are tons of videos online. And with ANSYS, I think their student version, I don't think they require a student email. So I'll leave it at that.
How much did it cost for you to build the rocket that launched successfully? How much was the total cost to launch the rocket that landed, that flew successfully? And how much total money have you guys spent or raised, if it's not a confidential question?
So total money spent today in all of AeroBing's history is a little bit north of $110,000 for everything, right? That's not necessarily just rocket motors. That's all of the equipment we have, all of the stock, basically A to Z, everything that we have. How much the rockets cost? It's gonna sound like a big number, but in the scheme of what we do and like what it would cost to buy this stuff commercially, it's astronomically low. This past rocket, I think just for the bill of materials was around $4,500. After travel, logistics, and everything else that went into it, turned into around $10,000. So both a lot of money and not a lot of money for what we do.
All right. So before we started our program this evening, I asked about where you guys were in your educational pursuits, and you're both seniors. So you want to tell us what happens next for you?
Yeah, absolutely. So following graduation, I'm moving to just south of Austin, Texas, to work for a company called Crossbow Systems, and kind of doing rocket motors and pursuing my AeroBing dreams.
Excellent. And?
I will be going to NYU to conduct my master's in mechanical engineering. I will continue to do my lovely simulations there, and yeah.
All right. Well, thank you. Thank all three of you for coming up here and sharing your successes and the route that you took to get to those successes. I'll also say that right now the International Space Station is just about coming up with a horizon. So, and we do have some. I think the astronomy club, they call them sucker holes in the clouds. So we should actually be able to see the ISS as well as Jupiter. And so thank you all for coming. Next week we have our presentation is by Peter Klimas, who is a physics teacher down at Vestal, extraordinary presenter, and he's going to be talking about gravity. And so definitely want to check that out. So I invite you all to come outside, and look forward to seeing you. Thank you. So meet me right out front.